Hi girls, so this is the video for the higher level homework questions on chemical equilibrium, and we're starting off with 2018 question 9. So I'm just going to go through the theory questions for 2018 question 9, but then when I get onto the other questions I'm just going to go through the calculations. So you'll notice that the theory sides of this question are very repetitive. So as I said before, it's a really good question to do in an exam because there's only so many things they can ask you, and once you practice the calculations enough times, you'll get the hang of it. So part A just asks you to give your definition for chemical equilibrium, which is a state of dynamic balance in a reversible reaction where the rate of the forward reaction is the same as the rate of the backward reaction. So make sure you learn your definitions word for word and you'll gain all the marks for that. The next part asks you to do your equilibrium constant expression for the given equation. So the equation we're given is CO plus Cl2, and it is a reversible reaction and it forms COCl2. And you'll notice that each of these components are all gases, which is important for the next part of the question. But just for now, your equilibrium constant is your products over your reactants. So it's, and don't forget your square brackets, COCl2 over CO times Cl2, and that is part 2 of the question. That is your equilibrium constant expression. Part C then asks you to state and explain the effect, if any. So a common mistake in a question like this is you'll just state the answer, but notice that it says state and explain. So within each of these parts, there's 2 questions as such. So part I asks you to state and explain the effect on the colour of the equilibrium mixture if the pressure is increased by reducing the container size. So as I said already, you'll notice that each of these components are all gases. So from Le Chatelier's principle, you should know that when you have an equilibrium reaction with all gaseous species, if you increase the pressure on the system, the equilibrium will shift towards the direction where the least amount of molecules are. So in this case, it's going to shift to the right-hand side and it's going to form more of this gas here. So what you would say there for state is you'd state the colour change. So you'll see in your exam papers, you're given this formula here and you're told that this is colourless, this is green, and this is also colourless. So obviously on this side, if you have a mixture of something that's colourless and green, it's going to look green on this side. And then as it goes towards this side, it's going to become more and more colourless. So for your answer there, you're going to state that the green colour fades away, or that it goes colourless, whatever way you prefer to say it. And then you're going to have explain as a separate point, and you'll use your, according to Le Chatelier's principle, the higher pressure favours fewer molecules. That's all you need to say for that question. I won't write it out, but the point that I'm trying to make here is that you need to write state and an answer, as well as write explain and an answer. You can't just give one answer for that question. Part 2 of that then asks to state and explain the effect on the equilibrium yield of phosgene gas of using a higher temperature. So this is your phosgene gas here. So straight away you should know from Le Chatelier's principle, a higher temperature will cause the equilibrium to shift to the left. And that means that if you increase the temperature of this reaction, then you're going to have more of the reactants formed instead of more of the products. So in general, we know that if you lower the temperature, you're going to have a higher yield of the product. So in this case, if you have a higher temperature, you're going to have a higher yield of the reactants and a smaller yield of the products. So for that one, you'll say state, and all you need to say is you'll have a smaller yield of phosgene gas, and explain, well, according to Le Chatelier's principle, higher temperature causes the system to shift equilibrium to the left, i.e. more reactants are produced, or you can say that in your own words. And then part 3 asks us, state and explain on the value of the equilibrium constant of using the charcoal catalyst. So again, you should know from Le Chatelier's principle that adding a catalyst has no effect on the equilibrium constant of reaction. And explain the catalyst does not affect the concentrations of any of the species. It only speeds up the time it takes to reach equilibrium. That's what a catalyst does in this situation. So that's part C then complete. So then we move on to our calculation part. So we'll leave this reaction up here. We'll do our ICE. So ICE. So again, I stands for initial conditions, how they change, and at equilibrium. So we're told that we have a 12 litre container. So I'll just write that up here, that it's 12 litres. And initially we have 0.2 moles of CO, and we have 0.2 moles of Cl2 initially, and that means we have 0 moles of the phosgene gas initially. So initially we have 0.2 moles of this and 0.2 moles of this thrown into a 12 litre container. We're told that we were asked to calculate the value of the equilibrium constant for the reaction if 85% of the chlorine gas had reacted when equilibrium was reached. So we're told that 85% of this 0.2 moles is going to react. So all you need to do is to calculate 85% of 0.2, and the way I do that is I just say 0.2 multiplied by 85, then I press second function and 1, and that gives you 85% of 0.2, which I don't know if you can see that there, but that's 0.17. So that means that 0.17 moles of the Cl2 that we're given here is going to take part in this reaction. Straight away then we know, because this is a 1:1 ratio, that means that 0.17 is going to react here. So from this 0.2 we're going to have 0.17 react there, and also again 1:1, so it's going to be plus 0.17 on this side. Don't forget your reversible reaction symbol. So that means it changes from 0.2 down to 0.17. So we're left with 0.03 at equilibrium. And same here, 0.03 moles of Cl2 at equilibrium. And over here, 0 to 0.17 is a change of 0.17 moles at equilibrium. So that's our concentrations. The next thing we need to do is change each of these concentrations to moles per litre. So at the minute, these are all still in a 12 litre container. And remember, we only carry out equilibrium constant equations in moles per litre. So I'm going to wipe this out now and move on to the next part. So to get it in moles per litre, we'll start off with our 0.03. And we know that there's 0.03 moles of this in 12 litres. So to find what it is in 1 litre, to get from 12 litres to 1 litre, you divide by 12. And what you do to this side, you must also do to this side, which gives us 0.0025 moles in 1 litre. And then we also had 0.03 moles of Cl2, so this is going to be the same concentration of Cl2. So we have 0.025 moles per litre of this, and we have the same amount of this, so we won't do it twice. And then the only thing we have left to do is find out the moles per litre of the phosgene gas. So we know that we had 0.17 moles of this in 12 litres. So to get what that is in 1 litre, we divide by 12, and we need to do that to this side as well. And that gives us 0.014167 moles per 1 litre. And it's really important in this question that you don't round this up, because in the marking scheme they have a very specific range of answers that are accepted, and if you round this, the final answer that you get won't be within that range. So just try to remember that when you are doing these questions, that you don't round these values. And the last thing then we want to do is figure out what the value is for the equilibrium constant. So we're going to sub in those concentrations that we'd worked out into our equilibrium constant expression that we did in part B of the question. So that works out as 0.014167, don't forget your square brackets, over 0.0025 times 0.0025, and that gives you a Kc of 2266.72, and your units then are going to be 1 over moles per litre. And then part E of the question, again, is a theory part. It asks us, it asks us to suggest reasons why low temperatures and high pressures might not be used in industry. And again, that's just coming from your theory. So as you know, maintaining low temperatures in industry is very expensive, and also if you use low temperatures and high pressures, it can give you a very slow rate of reaction. So we use our compromising values, which I talked about in the theory video. So that's that question there. So I do think that these types of questions are really good questions to answer in an exam, because there's not a whole lot of theory that you need to know. It's very, very repetitive every single year. So really, if you know your stuff on this, it's a very handy question to answer. Okay, so then let's have a look at 2017 question 7, again higher level, and this time I'm just going to go through the calculations. So this is 2017 question 7. So part B asks us to get our equilibrium expression. The formula we're given is N2O4 and 2NO2. So our Kc expression is going to be our products over our reactants with our square brackets as always. And this one goes to the power of 2 because we have that big 2 in front, over N2O4. And again, the square bracket's really, really important. That's part B. And then part C is our calculation, which I'll go through now. So again, our initial, changing, and at equilibrium. So we're told then initially we have 1 mole of this in a 10 litre container, and we assume then that we have 0 moles of this to begin with. Now, because this one is straightforward enough, I'm just going to change this into moles per litre now before I go any further. So I can change this into moles per litre just by dividing by 10. So if we have one mole in 10 litres, that's going to be the same as 0.1 mole in 1 litre. So you divide by 10 to find out what it is in moles per litre. So I'm just going to do that at the beginning because I think for this question it's more straightforward. So we know then we have 0.1 moles per litre of this. So we're given that Kc, in this case, is equal to 0.2. So this is one of those questions where we're given the equilibrium constant value and we need to work out the concentrations of the two species at equilibrium from what we're given. So we know that this is going to change by x, because we don't actually know how much it's going to change by. That's what we need to solve. And this is going to change by, so this is x, this is going to change by twice that because it's 1:2, so it's going to change by 2x. So from here to here, this is going to decrease by x. From here to here, this is going to increase by 2x. So then down here at equilibrium, we can say it's going to be 0.1 minus x, and it's going to be just plus 2x here. So the next step then is to fill these values here at equilibrium into our equilibrium constant expression. So that works out as that's going to be 2x squared over 0.1 minus x. So that's just subbing in the values that we worked out for equilibrium back into our equilibrium constant expression, and we can say that because Kc is equal to this is equal to 0.2, and then from there it's just solving for x. So what I did to solve for x here is I used the minus b formula. So if I rearrange this, it's going to be 2x to be squared is equal to 0.2 times 0.1 minus x, and that works out as 4x squared. And I'm just going to skip a couple of steps here, but you should get it to be 4x squared plus 0.2x minus 0.02 equals 0. So that is the equation you should end up with, and that is the equation then you're going to use in the minus b formula. So I'm going to say that this is A, this is B, and this is C. So you should be familiar with your minus b formula for maths, and I'm sure you're only delighted that you now get to use it in chemistry as well. So the formula, in case you're not aware, the one I'm talking about is the minus b plus or minus the square root of b squared minus 4ac all over 2a. So subbing in the values then that we had, minus b is minus 0.2 plus or minus 0.2 to be squared minus 4 times 4 times 0.02. So that's A and that's C, all over 2 by 4. So obviously, if you're familiar with using the minus b formula, you'll see that you're going to have two solutions for x, one using this plus here, one using the minus. So I've already worked out which one is correct. So in this case, using the plus is the correct answer because that gives us x is equal to 0.05 moles per litre. The way that I know that that is the correct answer is because we know that we started off with 0.1 moles of that N2O4. If we were to get that x was a minus number, let's say for example, or if x was equal to 0.2, that wouldn't make sense. So x has to be equal to something less than 0.1, because what x is telling us is how much of what we initially put in, how much of that is going to react. So if we only put in 0.1 moles of something, then we can't have something greater than 0.1 reacting. That wouldn't make sense. So if you use the minus b formula and you get two different answers, you're always going to use the answer that is less than the initial value that we're given. I hope that makes sense. If anyone doesn't understand that, give me a text on Teams and I can explain it again. But you might get it here now. I'm going to go through the ICE again, using the values that we've just figured out. So ICE, so we know initially we had 0.1 moles and we had 0 over here. We said that this was going to change by minus x, which we now know is going to change by 0.05. So this is what I mean here. If we got a value for x that was, say, 0.2, that wouldn't make sense because that would give us a minus number down here at equilibrium. So the value that you work out for x has to be either equal to or less than, in most cases, 0.1 in this situation. So we're going to be left with 0.05 moles down here. And this is a 1:2 ratio, which means that this is going to be 0.1. Just multiplying this by 2, and that gives us 0.1 down here. And that is the concentrations at equilibrium in moles per litre of each of these species. And that is the solution to that question. So lastly then, we're going to look at 2016, which was the last piece of homework I gave you on chemical equilibrium. But please do go ahead and practice as many past paper questions as you can on this topic, because as I said, once you get the hang of it, you're going to be really happy to do this question in the exam. So 2016 question 7, higher level. And again, just doing part C of this question because it's the only calculation part that there is. So part C, we're given the equation 2SO2 plus O2 goes to 2SO3. We're told that initially, so I'm going to put in our ICE, initially we have 96 grams of this, we have 24 grams of oxygen and 0 at the beginning of this. And then we're also told at equilibrium, we don't know what these are, but we're told that there is 112 grams of this. So I just wrote that out to make it clear for myself, but straight away we should know that we need to convert from grams into moles for this calculation. So I'm going to wipe this out, but I would encourage you to write it down if you haven't done so already for your homework. So the first part of the question asks us to write the Kc for the expression. So it's going to be SO3 to be squared over SO2 to be squared times O2. That is Kc for that reaction. And the next part then is to calculate the concentration. To calculate a value for that. So we're going to use our moles is equal to mass over M or formula. So the first one is going to be 96 over 64. So where we're getting this from is the mass that we were given for SO2 was 96 grams, and when you work out the MR of SO2, it's going to be 32 plus 16 by 2 to get 64. That gives us 1.5 moles. And that 1.5 moles is in a 50 litre container. So that's also something we're told in the question. We have 1.5 moles in 50 litres. So I want to find out what this is in 1 litre. So I'm going to divide by 50, and that gives me 0.03 moles per litre. Then for the second one, our moles of oxygen, we're told that we have 24 grams of oxygen, and it's O2, so it's 16 by 2 to get the MR. That gives us 0.75 moles in 50 litres. So to divide this by 50, we get 0.015 moles per litre of oxygen. And then I'll do the last one over here. At equilibrium, we know that we have 112 grams of the SO3, and that is over 80. The MR of SO3 is 80, and that gives us 1.4 moles in 50 litres. So you divide this 1.4 by 50 to get what it is in moles per litre, and that's 0.028 moles per litre. So that's the concentration of the SO2 initially, and the O2 initially, and this then is the concentration of the SO3 at equilibrium. So the next thing to do is fill those into our ICE table. So again, our equation is 2SO2 plus O2, which goes to 2SO3, and we know our ICE. So we know that we have 0.03 moles per litre initially of this, 0.015, which makes sense then when you look at it, because this is a 2:1 ratio, so this should be half of this, which makes sense. And we know here then it's initially 0. Then this changes, because then we know that this here is 0.028. We don't know what this is, we don't know what this is. So we're able to figure out that this changes from 0 to 0.028. So that means that it changes by plus 0.028 to get from here to here. And then because this here is 2:2, so that means that this must change by 0.028 as well. And that leaves us with 0.03 minus 0.028 gives us 0.002 moles of this have reacted, moles of this left over at equilibrium. And then we know that this is going to be half of, because this is a 2:1 ratio here, half of this is going to react as well. Half of 0.028 is the moles of oxygen that's going to react, and that is 0.014. So we take that away from this, and that gives us 0.001 moles of O2 at equilibrium. And then the last thing you need to do is sub in your values for each of these species at equilibrium in moles per litre into your Kc expression. So that is Kc is equal to 0.028 to be squared over 0.002 to be squared times 0.001. And that gives us 196,000 1 moles per litre. And that is the answer for that one. So you do get a lot of marks for those calculations. I would love to get some feedback from you girls to see how you're getting on with chemical equilibrium, if you're feeling good about it or if you're finding it difficult. Please, either way, let me know and we can see what we can do to help. So thanks very much.